Okay, so thanks for your indulgence. I just wanted to mention, we talked about the accelerating universe earlier. So every time you're in an elevator or in a car, you're part of the accelerating universe. Okay, you saw this field of view before. Nick showed this slide. I just want to point out, because I'm going to talk about stars. Kepler's was developed to look and find planets, but to understand planets, you have to understand the stars. And not only the stars that have planets, but all the stars in the Kepler field that we're observing, you get very great results about. I'm going to tell you a little bit about those today. And if any of you know the sky at night or know the galaxy, this is the Milky Way going across here, that broad band of a bunch of stars there. And these are the dark lanes here in the Milky Way. This is dust that's in our galaxy that's blocking stars from behind. So if the Kepler field of view would have been sitting on the Milky Way, you'd have areas with lots of stars and areas with no stars because the dust blocks most of the stars. But if you put the field of view up here, you don't have many stars. So it's sort of this compromised field of view to get a lot of stars, but not too many stars. So let me just jump into this. So I just want to show you some things about light curves, and this goes back to sort of the planet part. But over here is a picture, a drawing of what a transit of Jupiter would look like. So if you were outside our solar system and could see Jupiter transit across the sun, it would look very large like that. And the one at the bottom is Earth or Venus. It would look very small, just typically the planet size. So Kepler is a very simple experiment. All you need to know is the size of the star and the depth of the light curve, and you can tell the size of the planet. So for example, if Jupiter passes in front of the sun, you would get a light curve that looks like this. And this is a real Kepler light curve here. You can see the points on there follow the model, which is the line, very well. And the distance from this 0 level to the bottom of this, that change, is about 1%. And that's exactly the ratio of the size of Jupiter to the size of the sun. It's a real simple experiment. That covers 1% of the sun, so you lose 1% of the light. When you get to smaller planets like the Earth, as Nick was saying earlier, it's 1/100th of a percent. So now the light curve, which now looks far worse here, it's harder to find the small planets. This little drop is now only 1/100th of a percent. So it's much harder to find the small planets. But to understand the size of these planets, it's a ratio of the size of the planet to the size of the star. You have to know the size of the star. If you don't know the size of the star, you can't tell what the ratio is. So it's real simple, but you have to know about the stars. So we saw Venus. This is last transit of Venus down here. Here's Mercury in transit, so transits happen. Kepler does not resolve its stars and its planets. We see them all as a point of light, and we just see these drops in light. So you don't ever resolve it, but you assume that if something small goes around a few times and you see some transits, that it's a planet, and the ratio again gives you the size. So let's talk a little bit about the neat stuff that Kepler's doing in stars. And there's three sort of big areas that I try to group this talk in. The first one is this area of sort of astroseismology and stellar rotation. And astroseismology is one of those fancy words you learn when you get degrees in science. They tell you these big words you say in the public talks so that people think you know what you're talking about. But basically what astroseismology is you observe pulsations and vibrations that are occurring in a star. And those come out through the light at the surface of the star, but they're very, very low amplitudes. Our sun does this. It has this type of vibration called a P mode, and the P is very clever. It stands for pressure. It's a pressure mode, and it occurs on roughly a 5-minute time scale on the sun. And if your eyes were as sensitive as Kepler and you stared at the sun, every 5 minutes you would see its brightness change very, very slightly. And you could measure this brightness change over time, and you would see this 5-minute pulsation in the brightness of the sun. And from that pulsation, that very low-level pulsation, you could learn things about the interior of the sun. Because those pressure modes are inside the sun. They're not on the surface. But as those pressure modes bring pressure to the surface of the sun, they change its brightness slightly. So Kepler has allowed this same sort of analysis to be done on tens of thousands of stars instead of just one star like the sun. So that means that instead of only knowing about the inside of the sun, we now can learn about the insides of tens of thousands of other stars. So that's one real big area that Kepler has had an effect on. And the stellar rotation part is even simpler. If you know anything at all about sunspots and the sunspot cycle on the sun or the rotation period of the sun, you can watch the sunspots on the sun rotate around. It takes something like 25 days, which is roughly the sun's rotation period. Well, Kepler can see the effects of sunspots on, again, tens of thousands of stars, and therefore measure the rotation period of these
these stars. So it's really another great way to look and see how many stars are like the sun. Some might be exactly like the sun, and some might not be. So again, it's a very active research area that will continue throughout the extended mission. Another area is eclipsing binaries, and Nick hit on this a little bit, and I'll talk about them just a little more and show you some sort of animated movies of them to understand maybe what they are a little further. But the neat thing about eclipsing binaries is it's the only direct way we have to measure fundamental properties of stars, such as their radius, their diameter is easy, twice the radius. Caught you on that. Their luminosities, their temperatures, all sorts of the fundamental properties about stars. And while we knew about lots of eclipsing binaries before Kepler was launched, so it's not really so exciting that there's 2,400 new ones. That's a big number, that's a lot of them. But the exciting part is Kepler can observe these objects and get measurements of the brightness changes of these objects as one star eclipses the other. And those measurements can be so precise from Kepler's precise measuring ability that we can learn the fundamental properties of these stars to something like a 1% uncertainty. And that's just fantastic. If you ever want to know anything about stars, sometime in the near future, and even now, you will be reading things that came from stars observed by Kepler. They will just change what we know about stars in terms of their fundamental properties. And then this other area that I grouped together down here, emerging science. These are new things that were not able to be done before Kepler, either because we didn't even know these kinds of objects existed, or we just didn't have the highly precise measurements to do these. So I can now show you the cool movie. So this is obviously a movie of an eclipsing binary over here, and this is a Kepler light curve over here. And this light curve is really a set of data points that have uncertainties on each of those data points. But the uncertainties are so tiny that they're smaller than the size of this black line. The Kepler light curves are just phenomenal compared to anything that's ever been done before. And this particular system, I can show you thousands of these. This is a system called a contact binary. And you can see the two stars are actually touching each other. These two stars have a very short orbital period, and they're actually touching each other and sharing material between their atmospheres. And you can, once you get really tuned into light curves, you can see that each of these dips is roughly the same. So you don't know which star is in front and which star is behind because the stars are nearly identical. So this is one type of binary that Kepler can look at, a contact binary.
Do we know if it's one pulling apart or two coming together?
It's two stars, and whether they're pulling apart or coming together is probably really not known. Some people believe that these stars eventually will merge together and make a certain class of very rapidly rotating stars. Other people believe that they'll probably stay like this forever.
Is this science, was this part of the original Kepler mission, or is it bonus?
This is bonus. Yeah.
Didn't expect it when...
Well, we thought we'd see eclipsing binaries, but I don't believe anybody knew how many and what neat things we would learn from eclipsing binaries because of these very precise light curves. People did know about these contact binaries before. There were hundreds of them known, but nothing like this over here, where you can make really, really precise measurements. Now, another class of binary that Kepler has looked at, and this is a really interesting case here. So these two you can see are not touching. They're very different in size. And if you notice this light curve over here, you see that the eclipses, the times when one star passes in front of the other, change how deep they are. This binary has two stars that are not in a circular orbit around their center of mass, but in a highly elliptical orbit around their center of mass. Now, what that means is their orbital plane, so that is the plane of the orbit that's facing you where you see the eclipses, is tilted at an angle, and that angle, because they're an elliptical system with a third companion that you don't see here, that plane precesses around. So at times you see them at an inclination, which is this number that's running up here in this model. You see their inclination go from nearly edge on at 90 degrees to an inclination where they almost don't even eclipse anymore at about 70 degrees. And you can watch these stars do this over a time period of a few years. It's a really amazingly fast change for astronomy. And Kepler has found a number of these, and again, because Kepler's looking at them, not because they weren't known before then, but because Kepler's looking at them, you get these very precise measurements that you can understand the properties of these stars in great detail. If you don't know anything about sizes of stars, this is kind of a fun diagram. Here's the size of the sun, which is pretty big compared to the Earth. And these are the sizes of large and small stars called giants. So some giants are small giants, like this one here, and some giants are large giants, like this one over here. And Kepler has learned a lot about giant stars. And giant stars, again, were known long before Kepler was launched. There's many, many of them identified, but they weren't studied at the detail that Kepler can study them. And you remember I talked about those pulsations that occur inside of a star, these things called P modes. Well, there's another type of pulsation that's called a G mode. Anybody know what the G is for? You can't answer.
Gravity.
Yeah, there you go, gravity modes, right. So gravity modes are modes that work similarly to pressure modes, but they come from the very, very cores of stars, where the stars are incredibly dense, and at areas where the nuclear reactions are going on, the temperatures are very high. So not only can you measure P modes, you can measure G modes. And luckily for science, they don't look the same and they don't act the same. So if you measure one of them, you can say, oh, that's a P mode. If you measure something else, some other pulsational frequency, you can say, oh, that's a G mode. Well, it turns out that stars have different looking light curves that are combinations of P modes and G modes. And that can tell you stuff about the entire structure of the star. Not just the outer parts, but the inner parts, very near the core where the energy is being generated. So this is a star that's something like the sun. This is just a little bigger than the sun. And you see its light curve looks kind of like noise over there. So this is time going this way and brightness this way. So it looks like noise, but there's actually some signal in there if you analyze that. And then you have giants that are these red giants and things that are here labeled as a cleverly named blue giant. These are just larger giants or stars called supergiants. And they have different kinds of light curves. The bottom one you see has this very clearly dominant pulsating signal. Looks the same over and over and over. Where this one looks chaotic, it's a little more complex. It's a mixture of signals that co-add together and cause a more complicated light curve. Well, it's a movie, Nick. So if we try to look at what might be going on inside of a star, and look at these P modes and G modes. So this is clearly an animation. So out here in the outer parts of the star would be these pressure modes, and down here in the center are the gravity modes. And again, it doesn't look this simple for real, but the outside modes and the inside modes can be separated, which means you can learn about the outside of the star in one set of pulsations you see, and you can learn about the inside of the star in another set you see. So if you take these light curves and do something, again, one of these fancy science words called a Fourier transform, or a wavelet transform, and all that means is I figure out a way to tell you pulsations this way, this are in frequency, but it also could be time. So what are the time periods of various pulsations I see? For example, in the sun, I can see this one at 5 minutes. In some stars, you see one at 5, and one at 10, and one at 15, various time scales. And on this side of the plot here, you plot how strong those pulsations are. Do they change the amplitude of the light from the star by 1%, or by 10%, or by 50%? So it's the strength of the pulsations you can measure versus the period of those pulsations. And what I just want to show you in this diagram here is that this is a star over here this is a star like the sun over here. It's called a G-type star. So this is a star like the sun, and this is what its patterns of pulsations look like. This is the 5-minute P mode that we all know and love, or now that you all know it, you know it and love it too, that the sun would have. But if I look at a star that's a giant star, but it's the same temperature as the sun, that's what the designation G means. It has a pattern that looks like this. And so even if I didn't know what these stars were, I could tell that this star and this star are not the same kinds of stars. So we can do this for tens of thousands of stars and learn about the insides of these stars, where we can never go visit. You can't send a spaceship into a star or anything like that. So this is the only way we can learn about the inside of stars. And I think this is a movie too. So to show you one of the great things Kepler has learned, a brand new result that's completely unexpected. This is again just a size comparison of the sun to a giant. The sun rotates in about 25 days. Giants rotate in maybe 2 months to a year. They're very slow rotators because they're big. And that was known for a long time. What the unexpected result was, using these G modes from the deep interior is that the cores of these stars rotate much, much faster, up to 10 times faster than the outsides of those stars. And this has really given the theorists something to think about. They thought they knew everything about red giants. They thought they understood rotation periods, but this now is some more work for them to do. So if nothing else, we've kept 50 people, 100 people busy for the next 20 years. Anyway, that's just what the beginning like. It just keeps going like that. So if I take all these results of these giants, where I look at the rotation period of the outside versus the rotation period of the inside, that core, and I look at the sizes of these stars, so this is 3 times the size of the sun over here, out to 15 times the size of the sun over there. So these stars are all older than the sun, more evolved than the sun, bigger than the sun. And I look at the period of rotation of their core, so the inner part, how fast is it rotating? This is 10 days and this is 100 days. You see, and scientists love this kind of thing, you see there's a relationship. There seems to be a relationship here for the smaller giant stars, and then a relationship here for the larger giant stars. And this sort of break here, something happens at about 7 times the radius of the sun. And this is unexpected. Again, it's not something that we fully understand. And so the rotation of the core is faster, and we don't understand this sort of difference between these stars and why there's this sudden break. Because these giants, as they evolve, they get larger, and they eventually become these giants. So what happens right here to all of a sudden greatly slow down the rotation of their cores? We don't know. It's kind of one of those cool mysteries that Kepler is able to work on anyway, provide data that people can think about. Light curves, strange light curves. So planets are easy. You see a transit, another planet. Nobody cares anymore, right? No, not really. But you see light curves like this sometimes as well. So this is days down here. It doesn't matter what that unit is. This is 20 days to 60 days. This is 40 days long down here. And this is relative brightness normalized to this value of 1. So when you see a dip like that, it means that the object got slightly fainter. So there's a very complicated pattern of dips here, as you can see, including this kind of messy thing right here.
Is that actually a 5% dip?
That's right. So it's a 5% dip. So chances are these are not planets. 5% would be larger than Jupiter, right? Jupiter was a 1% dip. Very astute observation there. So right away you think these are probably not planets because they'd be too big. If it was a binary star, a simple binary star that was eclipsing, there would be a regular pattern of eclipses. Every time one star passes in front of the other, it would just be a regular nice pattern. So this is just a real mess. And we had 2 choices. One was to scream and run away and not do anything. That was the original thing we did. The second choice was to try to figure out what this is. A lot of work went into this next slide. But the best way we can model this, yes?
I'm seeing a meta pattern there, and I would call the mess something extraneous coming in on top of the base pattern.
You know, you guys should come and work with us. You're exactly right.
Yeah.
Here's what the best model that we can fit shows for this object. It is a pair, a group of 5 stars that happen to have all of their orbital planes perfectly lined up with the Kepler telescope. That we see all sorts of things eclipsing all sorts of things. And in addition, just for fun, because that alone would be too easy, this star here pulsates with a very high amplitude pulsation. So it's a star here that's bigger than the sun and more massive than the sun, and it pulsates much more than the sun's P modes. It has in orbit around it a pair of stars that orbit each other. And in orbit around these 3 is another pair of stars. So this is a really cool, interesting system. 5 stars that are all related to each other. They probably all form together, and they all have their orbital plane lined up to see that complicated pattern. So if you take this idea, and I say after a lot of work by a lot of people, you can model the light curve, that's the red line on here, and see how well you can model it, especially near that messy part, which I blew up here. It's not a bad fit. There's a little bit of stuff here that doesn't quite work, and maybe over there that doesn't quite work, but we're fairly convinced we're on the right track here for this really complicated system that you find. And if you find one of these, there's probably many more you don't find that just aren't lined up. They just don't have their orbital planes
So really a neat result. Cataclysmic variables, near and dear to my heart. These are objects that have two stars that orbit very close to each other. They have orbital periods as short as 80 minutes. These two stars are orbiting around each other. These are stars, not a star and a planet, but two stars. Some of them can be as long as 6 hours. So they're very short orbital periods. And they have these periodic times, these things here. Again, a light curve, time this way and brightness this way. So they have a fairly periodic change here, where material from one star that's so close literally falls onto the other star. Gravity pulls it onto the other star, and there's a big explosion that happens. And then occasionally, they have these longer explosions. And astronomers, as you may know, are great at naming objects. These are called outbursts. Seems pretty okay, they're an outburst, right? It's a brightening of by about a factor of 100 maybe. These, and here's the really good part, are called super outbursts. Very, very clever. So I want to concentrate on, I'm going to just show you some neat things we're doing with light curves. I want to concentrate on this little piece right here. This little piece right here during the super outburst has interesting things that occur there. I think if I do this, you can see them. So this is now a blow-up of that interesting stuff that happens at the top of that super outburst. And I think you can easily see here that it's periodic. I think you can see that the spacing of these pulses and these pulses and these little pulses is roughly the same. It's periodic. But what's not been seen in great detail before is the fact that while the spacing is periodic, the amplitude changes and the waveform, the shape of those pulses changes. So what we've been doing to try to understand this is, you can go ahead, Nick, is we've been producing sound files from the light curves. And so the first part of this is up here. So listen to this, because it's going to change, and your ears are going to tell you how it's different. So up and down, right? Okay, so Nick, you can skip somewhere to the middle.
All right. I have to do this complicated thing. Right there.
So now we're somewhere here. And you can hear it's very different. It's a very different waveform to a very different shape. And then one more time, so to that near the other side.
Like closing the counter to the 12th.
Yeah. So the neat thing about this is how astronomers used to analyze these data is they would look for periods in this, and they would find a pretty common period all the way through it and say, oh, we know it has a common period, there you go. But there's so much more information we have now, because it's not only a common period, it has these different shapes. And to understand those will take decades of what those shapes mean. But pretty cool stuff, so that's a lot of fun. And you can drive yourself nuts, and some people, like Roger, play this in his office all day and drive everybody else in the hallway. Okay, I think the last thing I want to talk about is a really neat thing that's come out of Kepler that's called relativistic beaming or Doppler boosting. And if you say relativistic beaming, people always get more excited because it has the word relativity in it. And so if you want to be cool, you say relativistic beaming. If you want to just be okay, you say Doppler boosting. So when you leave here, it's relativistic beaming. So what this is an effect that happens for objects that are moving toward you or away from you very fast. And in particular, objects that have lots of mass. So if I was a flashlight and I was moving towards you very quickly, I'm going to move toward them. You'll get over here. If I'm moving towards you very quickly, so if I have a flashlight, my beam of light coming out of my flashlight might be like this if I'm holding it. If I move towards you very quickly, that beam goes like this. It starts concentrating in the direction of my motion. Likewise, if I'm moving away from you, my beam goes like that and widens. That means that coming towards you, you see a little more light than you normally would if I was just stationary. And going away from you, you see a little less light than you would. Now these are tiny effects. And so the first real attempt to make this measurement was done from the ground using essentially the largest telescopes that exist, the Gemini Telescopes in Hawaii.
It was done over a 3-night period. So 3 nights of time on the largest telescopes is a pretty large allocation for a project. So you really had to convince people you were going to do something really cool. And what was found for this particular object here was a binary star of 2 white dwarfs, these very compact, massive objects orbiting around each other. They orbited around each other every 5.6 hours. And what you see, which, just believe me, this is really the Doppler boosting or the relativistic beaming, is you see this sine curve, and the black line is drawn there as a model to draw your eye to the belief that those points follow that curve. So you can believe it or not, the referees of this paper that we published, they believed it, so whether it's true or not. But you can see this here, the different colors are just the different nights of data. And you can see that there might be a sine curve here. And so this was essentially the first measurement of this Doppler boosting effect done with a ground-based telescope using a lot of time. And this particular change, so from that peak to this sort of 1 line, this 0 level, that change there was 1 part in 10 to the 3. That's a pretty great measurement from the ground. This is nothing. Kepler just, this will just never even be done again, because why would you waste your time? Here's a measurement from Kepler on, again, a binary star. You can look at this with your eye, right here and right here, and you can see the difference in those levels. The Kepler data is so good that you don't even need to solve the problem. You just look at the light curve and you can see it. This is a large star larger than the sun that has a companion star orbiting around it that you can't even see. The companion star is very massive, but it's so low in brightness that you could never observe it from the ground. The other star just completely outshines it. But if you use this technique of relativistic beaming, see, I'm getting into the fancy name now because it's cool. If you use that technique, you can fit this. The red line here is a model that fits that. And you can identify what this other object is. And this amplitude between there and there is now a factor of 10 greater than the amplitude in that first attempt from the ground. And it tells you not only the amplitude, it can tell you the mass of the object that's in orbit. Now that may not mean a lot to you, but remember when Nick was talking about the Doppler motions and you measure a planet orbiting a star and you can get the mass of that. But that's using a technique called spectroscopy. And in spectroscopy, you need to see these relative motions, and you need to usually use big telescopes and take a lot of time. But this technique allows you to, by fitting models to this changing amplitude, it allows you to get the mass of an object using only the light measurements. You don't need to use spectroscopy. You can use Kepler data all by itself and measure masses. This is a really cool thing. It cannot be done for many objects essentially at all before Kepler. And now over the next decade or so, this will be done for probably hundreds of objects. And we'll be able to measure masses of these things, including the masses of relatively large planets, which we have no real other way of getting their mass for. So this will be a really cool technique that happens. And I think that's the end for me. So if you have any questions, I have